you very much for giving me this opportunity to present our results on lithium-ion battery. I would like first to thank the organizer for preparing this conference, virtual conference, under this COVID-19 crisis. So I am talking from home. I'm sorry for the quality of the recording my talk. So according to the data in 2018, our energy sources are coming mainly from carbon sources. Around 90% are coming from fossil energy, and only 10%, maybe much more now, 10% are coming from some clean energy source. This is because the fossil energy are the cheapest one and are the most popular. But the big issue is that the fossil energy are running short, and people who are now trying to look for other sources, mainly solar and wind energy, to fit with the demand of energy over the world. So if we look at the electricity chain, people need to generate energy that people need, and we should deliver this energy where people need it, and also provide energy when it's needed. So the electricity chain is composed from generation, transmission and distribution, and storage. But in fact, we need a storage technology in the whole this chain. We need to have some storage technology during generation, but also during transmission and during the distribution and the consumption. So we cannot develop in the future any renewable energy source without developing an adequate storage technology that could accompany this development. So why lithium-ion battery? If we compare this technology with the other technologies existing in the market, normally we need to have a storage technology with high power and also with high autonomy for stationary and mobile application. And if you can see in this plot, the green side of this plot, we can conclude that lithium-ion battery can combine high power and high autonomy. This is the reason why this technology is now mainly used for electrical vehicles, for laptops, but also for storing solar or wind energy. So let me show you how lithium-ion battery is running. The lithium-ion battery is composed from a cathode side and anode side. In the anode side, we have mainly graphite, but in the cathode side, we could have some oxide, lithium cobalt oxide, for example, but also some phosphate and other component. So during charge process, lithium are removed from the cathode side to the anode side, okay, and during discharge, we have the phenomenon, the reverse phenomenon, the lithium are coming back from the anode side to the cathode side. So we have some reversibility of the process during charge and discharge process. Then the cathode material is the only component that providing lithium during charge and discharge, and the main research are now focused on the cathode side of lithium-ion batteries. But this is just a general explanation of this phenomenon of charge and discharge. But from scientific point of view, We have, in fact, three mechanisms when lithium is moving from one side to other side. When lithium, ionic lithium, are going to some solid electrode material on the anode side or cathode side. The first mechanism is integration or insertion. So we have lithium is inserted in the host matrix, which have monodimensional, bidimensional, three-dimensional structure, and lithium is forming only a weak band, so it's very easy to insert and to extract lithium during charge and discharge process. This is much easier, much more the more reversible phenomena during cycling of the battery. The second mechanism is alloying. Is normally seen in the anode side, where sometimes we use some metals as anode, like aluminium or tin or antimony. And we have this alloying. Lithium is forming with this metal some new alloy, lithium metal. We have huge capacity, but the problem, we have also huge volume change, which can be a drawback of mechanical stability of the cathode material, of the anode material. And the third mechanism is conversion. In the conversion, lithium reacts really with the electrode material to form a new product. This generally we form some lithium oxide as some oxide of transition ions. This is also a mechanism that can give huge capacity, but we have a new phase and we have some irreversibility during the first charge, discharge. Now let me to show you the motivation and the challenge of lithium-ion battery in the future. We need lithium battery that's providing high energy density, that could be charged at very fast current and having long-term cycling, could work in very wide temperature range and should be low cost. But the safety remains one of the main challenge of lithium-ion battery because of the many problems caused by this lithium-ion battery fire in China or in Japan or in some conference. And one of the factors that produce this fire or this safety issue is coming from the cathode material, which is generally oxide, and phosphate are now could be seen as the solution of this safety issue because of that oxygen is really strongly bonded to the structure and cannot intervene in the combustion of the electrolyte. So why phosphate? The phosphate material were introduced first by Professor Goodenough in 1976. Professor Goodenough is one of the 3 winners of Nobel Prize in Chemistry in 2019. And the structure of such phosphate are really very interesting from scientific point of view, but from also application. Because the structure is very, very stable. We have some octahedra, some tetrahedra, and we have this 3-dimensional network. We have also a wide range of space group from R-3, N-3C, or monoclinic C2/C. We have also some 3-dimensional pathway for lithium diffusion. But the problem of such phosphate is their low electronic conductivity, which is very, very big issue to use such material in batteries. But now we know how to overcome this problem by using some carbon coating on the particle of such phosphate. So I will present to you 2 examples that were recently published in two journals in 2019 and 2020. I will start by this nickel titanium phosphate. But before that, I would like to present to you the methodology, which start by preparing our material by using some simple and easy process. And after that, we use some characterization like XRD, Raman, SEM, TEM. And when everything is okay, when our material has some features, some encouraging features, we can use it in battery in the lab by using some coin cell. So this nickel titanium phosphate was prepared by using salt gel method, starting from phosphoric acid and some titanium and iron salt. The product was prepared first, and then we use a carbon coating process by using sucrose as carbon source. In fact, what we do, we mixed our phosphate with sucrose and we put in the furnace at 400 or 500 degree, but under inert atmosphere. And depending on temperature of synthesis, you can see the exercises show that if we prepare our material at 680, we got like amorphous phases, and at 700 we got decomposed material, but the best temperatures is to 670, which is the convenient temperature to get a pure nickel titanium phosphate. From structural point of view, we have a space group R-3, and we have some titanium oxygen O6 octahedra linked by PO4 tetrahedra. But the main important thing to say is the existence of some vacancies in the structure, which is a good thing for lithium insertion and for high capacity during discharge or charge. So we would like to check if we have really carbon in our composite. So we compare here the Raman spectroscopy of pure nickel titanium phosphate with carbon-coated nickel titanium phosphate. And by comparison, we can see in the carbon-coated the existence of the D and G bands that are characteristic of the existence of carbon in the composite. The amount of carbon was deduced from TG analysis, which is around 5.7%. TEM and SEM clearly show that we have some carbon layer on the particle, which is the M of our carbon coating. You can see more details in this paper with the reference in the slide. The second step is to use this composite as active material in lithium battery in coin cell. So we performed the test in two windows. The first one in the voltage windows between 185 to 3 volt, and second one between 0.5 and 3 volt. And you can see that in the both cases we have a good reversibility of the insertion extraction process. During discharge and discharge, we got 130 milliampere per gram in the first window, but we can reach more than 350 milliampere per gram during first cycles. The CV curves confirm that we have a good reversibility because the anodic and cathodic peak overlap during the 5 first cycles. But what we got a very fantastic result is when cycling our material during 1000 cycles. It's a very huge number of cycles. And under 10C or 20C regime, this means we use two high currents of discharge or charge. We have a good reversibility of the process during 1000 cycles. The capacity still maintained at stable number of 100 milliampere at 10C, for example. This is very interesting. That's also confirmed that we have phosphate are good, exhibits good structural and thermal stability during cycling. The second example that was just accepted in ACS Applied Material Interface journal consists of introducing lithium and iron in this nickel titanium phosphate. So we substitute some nickel ions by lithium and iron, and we obtain this formula. And once again, we use very easy synthesis method, and we got by XRD a pure phase as revealed by the Rietveld refinement here, and the structure is a Nazi-Con type structure with the space group R-3C. From SEM or TEM, we can clearly see that we have nano-sized primary particle but with heterogeneous carbon coating. We don't have a very homogeneous carbon coating, which should be optimized in the future. So from electrochemical cycling, we can see that we have, when cycling between 1.5 to 3 volt, the discharge, we have like a plateau at 2.5 volt, we have a reversible plateau, and CV confirmed also that we have a reversibility of the insertion and extraction. So for these two phosphates, we have the mechanism of insertion, no conversion and no alloying. This is the mechanism of insertion. Lithium is introduced to the structure. We have weak bending, and during charge, we extract lithium very easily, and we got reversible charge and discharge. We do the same thing during 1000 cycle, and you can see for two regimes, 5C and 20C, and we have in blue the charge capacity, and in red the discharge capacity. We have very, very good efficiency of the charge and discharge. We have the same capacity during charge and discharge during 1000 cycle, even at very fast cycling. Very fast means that very high current, very high powerful current during 1000 cycle of charge and discharge. This is really very short, briefly the results obtained, but we can check in the paper more details about the studies. So let me give you a conclusion, which is a really general conclusion on R&D on lithium-ion battery. So the aim is to have high power, battery with high power, high capacity, high safety, and low prices. For that, we should develop new materials, anode, cathode, or electrolyte, or modify the existing one by using new synthesis method or using new coatings approach. But we should have in mind that we should select a chemical element that can be non-toxic and could be recycled, could get recyclability when needed. For that, we need some new method, but also some modeling. Modeling is very important to develop new composition. We should have also new techniques, especially the in situ techniques, and we should understand the degradation phenomenon by using also some side reaction technique analysis and also many other approaches. So we should combine the expertise of chemists, of physician, modeling, on the electrochemist, and so on. It's really a wide range of collaboration between scientific from many topics. So at the end, I would like to thank my co-workers, Professor Katarina from Freiburg, and Professor Hisham Ben Youssef from Mohammed VI Polytechnic University, and Dr. Saadoune that just defended in last January for doing a great job. I would like also to thank our financial support, which is coming from OCP Foundation and from CNST. And at the end, I would like to thank you for your attention.